Hello and welcome to our 17th lecture of NPTEL course Introduction to Mechanobiology. So, in the last class we were discussing about dynamics of actin growth, right. So, we are talking about actin polymerization and we are trying to understand how can we quantify the forces associated with actin polymerization and the nature of force velocity relationships. And the calculating the magnitude of stall force. Okay. So, for calculating stall force experimentally, I had given an example where we used an AFM, where the probe, the tip was oriented perpendicular to direction of cell movement. Okay. So, and as a consequence you can track the deflection, okay, as a function of time, and you would get a deflection profile which is something like this. Okay. And the force, so once it plateaus, that means, so from this curve you can get the speed or velocity and the force as well. So, velocity is nothing but slope of this curve and force is k times deflection, okay, where k is the spring constant of the tip. So, with this what the authors found was you had a force velocity curve which looked something like this. So, it is concave in nature, the concave force velocity curve. So, and we wanted to ask that can we develop a modeling formalism for testing how various parameters contribute to dictating the nature of force velocity relationships. So, in that regard I had introduced a simple model where you have individual monomers, okay, which is constraint. So, you start with a filament of 3 monomers. So, this back wall is fixed, okay, and this filament polymerizes against a wall, okay, which is on which you exert a force F, okay, and you want to see what is the network dynamics of this growth for different values of branching rate, so on and so forth. Okay. So, the events that we discussed are possible is filament growth, or polymerization, depolymerization, and branching. So, let us assume the initial distance of the filament from the wall, this distance is d of wall, okay. And what you have another length scale which is that if you have a filament of certain, so you need a minimum distance of dBr before a new filament can form and branch from this point. Okay. So, in other words, so this is the minimum distance, which means that for any filament length L greater than dBr or greater equal to dBr, you have a finite probability of, or you have a finite branching rate. So, it is not necessary that as soon as an existing filament becomes dBr, reaches a length of dBr, the next filament has to branch. So, as a consequence of this you can have multiple branching events. Okay. So, if my DBR in this case is 4 monomers, once I have 4 monomers I can theoretically form another filament which grows horizontally, so on and so forth. Similarly, from here for the existing filament to grow I can have another situation where a filament branches like this. Okay. So, you have a branching rate of KBR, which is the branching rate. So, the polymerization rate can be given by R on. Okay. Okay. So, if K0 is the intrinsic polymerization rate, you have a concentration C of the monomers and exponential minus f d by kBt is the K on. Okay. So, this is the polymerization rate. So, what we have here is an exponential dependence on force F, which is with which the wall is being restrained. Okay. And d corresponding to the distance the wall moves if a monomer gets added. So, for the case of a straight filament, let us say your d is nothing but equal to delta, where the delta represents the monomer length. But if you have at an angle, okay, then d is equal to delta cos theta. So, this angle theta is 70 degrees. Okay. So, we want to study the growth of this actin network. For that we use Monte Carlo simulations. Okay. And specifically we use an algorithm called Gillespie algorithm. Okay. So, in Gillespie's algorithm what you do is, so you have the total number of events. So, let us say what are the events? You have total number of events as n polymerization events, n depolymerization events and j branching events, where j is less or equal to n, okay, where n responds. So, n is the number of filaments. Okay. So, I can calculate the probability of an event P m as K m by summation of K m over I equal to 1 to 2 n plus j. Okay. So, given these probabilities, so what I do is in Gillespie algorithm, in each time step only one event is triggered. And the time after which the next event is triggered, delta t, okay, equal to is given by 1 by summation of all rates into log of 1 by r, where r is a uniform random number between 0 and 1. Okay. So, using this, okay, so let us see what we can simulate. Okay. So, let us begin by for the case of a single filament which is polymerizing against a wall subjected to a force F, okay, and this filament is horizontal. Okay. So, for I can write the expression for speed or velocity of the filament, okay, or velocity of filament growth as k on C. So, k on is k 0 into C into e to the power minus f d by k t, okay, minus k off. Okay. So, once we have this particular expression, so this is the velocity, right. So, stall force, I can determine the stall force for this particular. So, first of all, so the velocity profile will look something like this, exponential, right. You have an e to the power minus f d term. Okay. So, this particular value, okay, at which v is 0, okay. So, f corresponding to v is 0 is called the stall force. So, I can set v equal to 0 in this expression, and I can have k 0 concentration of monomers e to the power minus f d f s d by k b t minus k off equal to 0. So, from here I can find out the value of f s. Okay. So, I can find out the value of f s. Okay. So, this will turn out to be k b t by d exponential. So, you have k off by k naught c at the log into log of something. Okay. So, this is some intrinsic force scale, you can call it f naught. Okay. So, if you plug in the values for an actin monomer system, you will get f s of the order of 1.97 f naught. Okay. So, now let us see how will the force velocity relationship look for a network Okay. So, let us say, so you have two length scales here, one is d wall, okay, which is initial position of the moving wall from the fixed wall. Okay. So, this distance is d wall. Okay. So, I think earlier I had represented this distance as d wall. You can choose either way, because you know that this is the length of initial length of the filament is 3 monomers. Okay. So, it does not matter. And what we have another length scale is dBr. Okay. So, dBr is the minimum distance between two branching points. Okay. In other words, if I have a filament growing like this and a filament has branched at this point, there is a minimum distance beyond which another filament can branch from here. Okay. So, this distance d prime has to be greater or equal to dBr. And what is the physical significance of that? One possible reason is this branching event is mediated by a protein called ARP23. Okay. And the size of ARP23 has been estimated to be of the order of 10 to 20 nanometers. So, if you have a big protein sticking to this point, there is a likelihood that the next binding zone will be some distance away from this binding point. Okay. So, you have dBr and d wall. Okay. So, now imagine the simple case. Okay. You have this system, you have one rate of branching rate, k 0, c, everything is given, d wall is given and dBr is given. Okay. So, let us assume dBr, okay, as 100 times delta, where delta is monomer length, and d wall is 10 delta. Okay. So, what this suggests is that the wall is only 10 delta away from the back wall, while it takes the filament has to be 100 delta in length before a new branch can form. Okay. So, if I look at the velocity versus force curve for the single filament, okay. Single filament. So, this is corresponding to horizontal filament, single filament without branching. Okay. So, it is obvious, or one would anticipate, that if I operate, if my stall force, let us say this restraining force. So, this is F s corresponding to a single filament, okay, this value. Okay. Now, imagine I am operating with a force value equal to the stall force of a single filament. At this force, it is unlikely that the filament will grow to reach a length of 100 delta. Okay. So, the value for this curve, for this system, here you will have the same value of the stall force, okay, and beyond also it will be 0. Okay. But imagine that if the force on the wall is less than the stall force, okay, let us say we are operating somewhere here at this value of force. So, there is a possibility that a single filament will keep pushing the wall further and further, okay, till you reach a distance of 100 delta, such that a new filament can form. Okay. And once a new filament is formed, you have two filaments pushing against the wall. So, the stall force of that network is expected to increase. Okay. So, you will realize that this will have a curve, okay, something like okay. So, you have a force curve for a single, starting from a single filament. If you have one branching event, you will begin to see for dBr equal to 10 delta, dBr equal to 100 delta and d wall equal to 10 delta, you will get divergence of the force velocity curve from this single filament case. Now, let us assume, okay, now let us assume I have dBr equal to d wall equal to 10 delta. Okay. What kind of a force curve may I expect? So, in this case, the branching distance is exactly the same as the wall distance. Now, given this particular phenomena that we just discussed, you are almost sure that that a new filament will branch. In that case, it turns out you will have a force velocity profile. Okay, it will start from here and it will have a force velocity profile like this. Okay. So, the presence of branching or the occurrence of branching really shifts the stall force to higher and higher forces, because you have systems. So, you can have various geometries. Let us say one geometry is this kind of case, okay, where you have two filaments pulling. In this case, if you have a third filament which forms, then again the stall force will increase. Okay. So, this suggests, now let us see why is it for back to this particular case, okay, where dBr equal to 100 delta and d wall equal to 10 delta. How did we deviate from this particular case? So, to understand that, if you plot the position of the wall, okay, if you want position of the wall as a function of time, okay. So, if you plot it as a function of time, you will see these wide fluctuations are there, and let us assume that this length, okay, this length is equal to either 10 delta. Okay. In that case, multiple number of times 10 delta or 15 delta, you will see every once in a while the position of the wall is much beyond this distance at which branching is triggered. So, once every time for these events, when the wall position gets pushed beyond the branching distance, there is a new branching event. Okay. Branch will form or may form, because you have a finite probability. Okay. And once a branch is formed, the stall force will increase, because now there are two filaments which push against the wall. So, in this case, so if you were to completely suppress this fluctuation dependent phenomena. So, this is an example of fluctuation determining the stall force. Okay. So, if you were to completely stop any growth of filaments or branching, you must ensure that the fluctuation for one particular case, even with the fluctuation, it always remains below this particular case. So, in this event there will be no branching, because even with fluctuation you do not surpass the branching distance dBr. Okay. So, you can also understand this effect of fluctuation by plotting the number of filaments, okay, contacting the wall. Okay, as a function of force. So, let us say if my force was 0, okay, if my force was 0, okay, this is the value of 1. If my force was 0, I am starting from one filament, okay, and because there is a single filament which can grow against 0 force, the filament will keep on pushing the wall more and more. So, even if you whatever be your value of branching distance under 0 force, even if you have a branch getting created, the branch will never get in touch with the wall. Okay. So, the number of contacting filaments will remain 1, okay. But as you increase the the force, you will see an increase in the number of contacting filaments, because this filament, even if it pushes the wall, it will push so slowly that the branching filament can actually grow under no force conditions and then catch up with the horizontal filament. So, eventually for every case you will see a drop. So, this corresponds to the stall force. Okay. For another case, so as you increase the branching distance, you will see that these curves will keep on going up and up. Okay. So, this is let us say lowest dBr value, okay, dBr 1, dBr 2, dBr 3. Okay. So, if you use the smallest value of dBr, okay, so as you increase the values of dBr, your curves will shift up and up. Okay. So, you see how this system can change and how the stall force of the system is determined by the branching architecture of the network, and which in turn is dependent on dBr and dwall. Okay. So, what will be the growth profile of this network? Imagine that I constrain the total number of filaments in the system. Okay. N filament is the total number of filaments in the system. Okay. So, what you will see, okay, in the force velocity curve, what you will see, so this is again the stall force for a single filament. What you will see is, as you increase the stall force, okay, let me color it, as you increase the number of filaments, sorry, not the stall force, the number of filaments, you will have curves which look like this initially, and eventually, okay, this direction you are increasing the number of filaments. Okay. So, from the profile you see that as you increase the number of filaments, Beyond a certain value of NFL, your curve is concave. So, rightmost end is concave, leftmost end is convex. Okay. Increasing the number of filaments will make the force velocity curve more and more concave, which means over a wide range of forces, okay, in this range cells can protrude in a force independent manner. Okay. So, when you increase the number of filaments in the system, okay, the number of contacting filaments as a function of force. So, okay. So, this is with increasing in the value of NFL. Okay. So, increasing the number of filaments will lead to increase in the number of number of contacting filaments also, but beyond the stall force you see there is a sharp drop. So, because the first filament itself will not increase, will not branch. Okay. So, with that I end here. So, just to conclude, there are two important messages. Okay. Relative ratio of dBr to dwall dictates the nature of force velocity curves. This is one, and the second one is filament orientation also matters. Because even if you have only 3 filaments in the system, this is one particular geometry versus this might be another geometry. Okay. So, there will be difference in the nature of the force velocity curve depending on what is the geometry of the filaments. I thank you for your attention.